Hello and welcome back to Old School Coding, where I'm using the tools of the 90s with the behavior the practices I did in the 90s and the languages I used in the 90s to build a 1990s style microcomputer simulation. So we've done a whole bunch of things, and our next thing I want to do is I want to look at the Arithmetic Logic Unit. This accounts for a number of the bulk of the opcodes, the largest bulk of opcodes that we haven't done so far, because we have part of the opcode is going to be selecting what logic or arithmetic operation we're doing. And another part is going to be selecting what register to operate from in conjunction with the accumulator. So we have another one of these cross-product situations, like the move instruction where we move from one of the 7 registers into one of the 7 registers. Now we have ALU operation where one of the operands comes from one of the registers, and the operation is one of several operations, and the result, of course, goes back into the accumulator. So the architectural features we're going to use here, we've got the accumulator, which is going to be held in an accumulator latch. We'll be selecting an operand, which will get dumped into this temporary register, and then we will perform an arithmetic operation, and sometime in the future we are going to take the result and put that back in the accumulator. So let's take a look at not the timing. Here are the ways that the t-states fall out. Let's take a really simple one. Add a register to the accumulator. So this is 8 instructions really. We're going to ignore references to the M operand for now. We'll get everything else working first. We'll bear in mind that we have an M operand, and let's look at the general thing. So we do the instruction decode here, and in T4 we want to get the current contents of the accumulator latched into the ACT, which is the accumulator temporary register, which appeared below the accumulator on that diagram. We may be able to get away without using the ACT. I think ACT is always the same thing as the accumulator. No, let's use the ACT. And the second operand of the instruction goes in the temp register. So we need to have temp and ACT present. We will obviously we'll need one kind of cycle that just selects this. So this M1T4 is just marshalling the operands, and it gets both ACT and temp unless temp needs to come from somewhere else, which will come later on. That's like if we're reading M or if it's an immediate. And yes, there are, for add, for instance, we have add register to accumulator, we have add memory to accumulator using HL as the address, and we have add immediate, which gets the data from the instruction stream. I think we can set up the framework, and as long as, for this, and as long as we recognize that the temp register may be set elsewhere, we can divide our work up. The other thing I've noticed here is that all these guys have a final bit of work that happens in the T2 state. Now, this is footnote number 9. Let's look at it. Footnote number 9 says, the results of these arithmetic, logical, or rotate instructions are not moved to the accumulator until the state T2 of the next instruction cycle. That is, A is loaded when the next instruction is being fetched, and this overlapping of operations allows for faster processing. Well, that's true, because in the hardware, go back to here, let's take a look at add from memory. We've got data coming in here in M2, well, M2 or T2 or T3 of M2, which means that we need to have some time to do an add, and that might take a while. So what they do is they say, well, we're going to take the results of the operation and we're going to latch it back into the accumulator here. So I need a general mechanism to say, please call this T-state management routine during T2 in addition to anything else you're doing in T2. So not as a substitute for the T2, but in addition. And this needs to happen in all of the M1 T2 states. Okay? So we're going to need that table. This happens in T2, so T3 IR gets loaded, so we still have IR set. I think what I'm going to do is I'm going to set up a generic table for M1 T2 operations based on IR, based on the prior IR. Think of it as a sweep up at the end. And in case there's anything else, I don't think there's anything else that uses it other than the ALU, but I will set that up. So we'll need that. And I can actually base that based on IR, so nobody else needs to do anything. We'll just make sure that ACT and temp are loaded up before we trigger the return to M1T1. I will want to check and make sure that this is serviced when we're taking interrupts. So we'll want to watch out for any of the other M1T1 cycles where we have an M1T1 generic. We'll need to make sure that it's T2 services this. So what this comes down to is setting that mapping up, and that'll actually do the ALU operation. So then we need to set up our operands. For ALU operations, I believe that it's always ACT is one of them. We can look at this, ACT, yada, yada. Let's identify these instructions that are using the ALU. Add, obviously, ACT plus temp. ADC is add with carry, so we need a carry flag. Aha, we need to set up our flag word now. We also need to set our flag word. Sub with borrow. Now increment register does not use the ACT. And in fact, the increment register stores the result here in this T5 cycle. I'm not sure why they didn't put it out here in the same way they did these guys. They could have, and it would have shaved a T-state off of those cycles. So increment register and, increment memory is going to be wild. Decrement register. So these guys won't use the trailing T2 sweep up. Decimal adjust accumulator, so we will need to collect the half carries. This is the carry out of the bottom nibble of the operation. That's a little extra work, which I will conditionalize because in practice, in all the work I did with the 8080 series, decimal adjust was an extraordinarily rare thing. And if we can avoid doing it, then we can avoid doing extra operations to determine the carry and to store it and so on. I'll write the code. I'll tell you what, I'll write the code and then I'll put comments in saying, comment this out if it turns out to be a hotspot. We have logical operations and register, again, ACT. This is written with A+. This is a ANA, which is an AND accumulator, and they've written it with A+. Yeah. XRA. So they're writing plus here for the generic ALU operation. That may be a copy-paste error, or it may just be they didn't want to figure out operations. They do write CMP, they do write minuses. Or a, now CMP sets the flags and does not store the accumulators, so that will all be in this sweep up code. Rotates are gonna, that's interesting. Notice here that this says we're doing the rotate here, so I am going to have a register called ALU. Okay, so we need a ALU, we need a temp, we need ACT. I think we already have temp. Complement accumulator, CMC, these guys, CMA apparently doesn't use the ALU. I will have to look up and see if it adjusts the flags. Store carry, these are not. We have a number of conditionals that use the flags, and that's it. Okay, so let's, And during that time, I didn't show you the PDF. Let me bop the PDF up on the screen and just display that really quick, what we were looking at. Okay, so we have ALU instructions starting about here. And this annotation right here, this 9 footnote was saying this is actually the M1 of the next instruction we do this in. Okay, so temp and ACT get loaded here, and then we do the ALU operation and store it there. And that's all normal. And then we have things like increment register where we're saying temp plus 1 is into ALU. So we do actually have a latch called ALU, which will go out to the data bus. So all these things, if it says ALU, we're going to dump it in this byte called the ALU, this observable thing called ALU. And again, the compare that I was talking about here, you notice this says ACT minus temp set flags does not latch the data, does not latch the result into the accumulator. It doesn't even latch it into ALU at this point. Although I will probably latch the result of the subtraction into the ALU so that I can also latch the results into flags. Okay, turn off the PDF. And now we can go start adjusting the state of the CPU to include all of that traceable information we need. Hold on, I want to decrease the size of the window here on my screen. So I'm actually keeping the PDF up on my screen even though I'm not, it's not the recording, because this recording is probably about half of my viewable screen space. Of course, I've got things like OBS up on parts of it. Okay. Oh, between sessions, I did push all of the source files down into the source directory here. So we've got all the .c files. And then I said, well, let's take all the test code and put it in the test directory. This means that if I run test coverage, I can run code coverage analysis after I run my tests. I can run the BIST, and I can say, give me code coverage on just these files. And that gives me the bona fide lines I have not covered that I intend to test without actually covering lines that are specific to testing or benchmarking. So these test files include the post, they include the BIST, and they include the bench. And we've got our flags noted here because I made a mistake. I didn't have these flags in mind, and I was seeing higher and higher numbers here. And I was saying, well, okay, we're doing real work now, and I can't make it much faster, but it turns out that you've turned the optimizer back on. It does a great job. So we want to go to the headers here. And 8080 has some more state, which we're going to have to initialize. So we'll bring up 8080.c here. So first of all, let's add the registers that I'm missing, internal architectural features, that is. Stepping back to the block diagram, I'm going to try to use the same names. We have the accumulator here. We do have the temp register. We're going to add in the ACT, accumulator latch, for ALU operations. That's to keep the inputs to the ALU stable while we're latching new data into the accumulator. I may or may not need that, but I'm going to expose it so that we can watch the model of what data is flowing into and out of that latch. And on the block diagram, that's between the accumulator and the ALU, and it's got a line coming from timing control that controls what happens with it. So ACT, we have TMP, output result of ALU operation. Okay. So IR, temp, accumulator, latch. I'm going to place these in a slightly different order. No, I'm not. Let's leave them let's leave them, it's not important. So in it, we do need to initialize these new signals. I don't think I initialized temp. I did not initialize temp. Let's try this again. We have IR. We need to add those three. So, search for semicolon, kill it to the end of the line. Go to the beginning of the line, I'm at P. Okay, so we've got that. And now, of course, we're getting ALU, ACT, and temp are not actually used anywhere. Well, that's correct. I do need to initialize them. So we're going to come down here, and I'm going to do data init. Try this again. Scan for equals. Trim that part off. Find the white space, keep that part. Data, init, that, format of %s. So that initializes that. So the invariants, we are going to want to do data invars for these three. This is temp, ACT, and ALU. What else do we do with IR? That's it. So now we need to add support for these to the test file. Okay, so that's all laced in. So now if we manipulate these, then they will appear in our trace output. So that got our architectural state. The next thing is I needed to have a way of regaining control during the second T state of the machine cycle of the next instruction. And I think I'm just going to do that as another one of these tables. Opcode decode table giving the T-state function to use for M1, T2. Sweeping result up. Last bit of work for prior instruction. Okay, so there's M1, T2. Then we need to go back here, and whatever we do with M1T4, we're going to do something similar for M1T2. And the difference is we're going to initialize it to a null pointer, because during M1T2, we want to know whether to do this or not. And I don't want to dive into state power on or compare with state power on. I just want to say if it's a null pointer, we don't do it. And that's all we do with M1T2 in this guy. Everywhere else, it just deals with it. So currently, the only machine cycle 1, the only M1 we have is this guy here. So what I'm going to do is during phi2 rise, I'm going to do a M1T2 This is a generic 8080 thing. It's going to occur in multiple places. So a lot of this occurs during every M1T2 cycle. So I think if I start getting support for more of them, for instance, the interrupt stuff, what I will do is I will try to abstract this out and make callable subroutines, which as long as you're not calling through a pointer, you're not blowing the pipeline. So we'll just put this in line for now. This is a P8080 state M1T2. We don't even want to peek at it until here, so we say M1T2 is equal to CPU arrow M1T2 sub CPU arrow IR arrow value. Now, the other thing I could do is just have this always, have M1T2 point to a no op. This would mean we're always blowing our pipeline at that point. It's more expensive. A call through a pointer to a no op or a test for a pointer null. I think a test for pointer null is cheaper. And instead of using 0, I am going to actually say null. Make it easier to say, yes, I do understand this is null. I am doing this on purpose. Don't tase me, bro. And segmentation fault, because of course there is. CD projects, live coding, run bit. Let's just say run. This says we are in clock run 1, edge 2, subs run, on oscillator rise, edge 2, sub run. We're here in state PC Inc., line 63. So M1T2 is not null. However, it is null. How about if I write this as a not equal? That's better. So we know we're getting there. And we know that we're seeing the null, and we're detecting the null, and we know that we're skipping the null. So now, if we fill in an operation here in M1T2 of IR, like we saw on the table, then it'll get executed, which means it will be picking up data from these registers that we set up. So back to source. I'm going to say i8080 underscore ALU.c. here looks something like mauve, but not exactly. Eventually, ALU will probably manage all of them one way or another. But for now, I'm just going to say many. This implementation, very similar. This implementation uses one M1 T4 function. I'll write the comments later. So basically, during M1T4, for most of these instructions, what we want to do is collect the SSS register and put it in temp, and collect the accumulator and put it in ACT, which means we need one of these for each SSS. So I'm going to do something very similar to this. This is M1T4 I'm setting up. It's not state MOV T4, it is state ALU T4. Like that. Okay, so now we need one of these functions. We need to actually implement the various functions that we've defined here. And we need to set up a init. We are peeling off. Let me look at the add instruction again. We have SSS is a low 3 bits, so that's good. .T4 continue. We do not have a DDD. The op is oh boy, I need to do this for each ALU op. So just for my own ALU operations. Going to copy this in from the PDF file line by line on my own. So this is OX80 plus SSS is add R. OXC0 plus SS is ADI SSS comma immediate, which we are not going to handle yet, but I want to log it here. ADC is OX88 plus SSS. I'll sort these by operation code later. I'm putting them in the order they appear. This actually includes SSS being 6. Read of memory at HL. And that goes for all of these. So on the PDF, it actually has a separate line for them because it's a different layout. No, let's write it separately. Each L and 111 equals A. Six is add M. Do I have a C6? Do I have an ADC? Okay, I do not have an add immediate of data to memory to end the register. So we do need to separate those out. So add M, ADI data, oh, silly me. You don't add to a register. You're always adding to the accumulator. So we're adding the register, we're adding memory, or we're adding the immediate. Fine. ADC is that. ADCM is OX8E. This is ACI. Yeah, let's start collecting these together by when I am likely to implement them. Sub. Instead of 8, this is OX9. In fact, let's not worry about the rest of them. It begins to get crazy if I include those. A0. And keeping the table this narrow helps figure out what's going on. Let's see, sub M is 98. SBB. There we go, 98 is SBB. I think INR is completely different. OX04 plus DDD times 8. Yeah, because the output doesn't go into the accumulator. Let's ignore the ones that are INR and so on. IX, DCX, DAD, DIA, those are not ALU ops. And now we get back to OX. A0 is ANA. A8 is XRA. B0. One step at a time. The table is filling out nicely. B0 is ORA. This is CMP SSS. So CMP uses all the same logic. It just doesn't write back to the accumulator at the end, so otherwise it's a subtract. Okay, 8, 9, A, B. This is 8 of them. So what we really have here is 3 bits of the instruction specify which opcode. So it's 8-0 with 3 bits for the opcode and then 3 bits for the register. And we're jamming in the function, which will, we then need to also say, P8080 state M1 T4 is equal to that. If null not equal to M1 T4, there. Now I didn't actually, yeah, I did use that down here. So I'm just going to call this T4 so it's like the other one. No, I better call it M1T4 because that is a valuable cross-check. Also means that up here I should be calling these M1T4 and M1T5. There we go. Okay, so we now have a whole bunch of warning used but not defines. Well, that's because I need to do an implementation now. And we need to figure out what it is we are doing during these guys. So let's go look at the PDF page. I'm not going to put this on the screen because we have looked at it before. Basically, for add A, during T4, we want to put the source register in temp and lock A into the ACT. So this is data 2, temp, CPR value, so it's the same thing. We also want to do a data 2 of CPU arrow CT and CPU arrow A arrow value. And I'm not sure why my editor was trying to indent that data 2 so far. Now, all of these guys have no M1T5. So M1T5 would be used for things like incrementing a register or register pair or so on. So we do not have that. However, this is the last T state. So we do need to grab the ret M1 int and raise that during phi1. So ret M1 int needs to be set during the entire cycle. This says we will go back to a normal M1 T1 cycle after this guy. And that is true for these instructions. That is not going to be true for instructions that have an immediate operand. It is not going to be true for instructions that read from M, but for these, it's true. So this is these 8 operations by these 7 registers. That's 54 out of the 256 opcodes. Pretty good chunk. Again, I will write the comments later so I can wordsmith the English a little better than I can do while I am streaming. So I have done this. What I also want to do is arrange for the actual ALU operation to go into the M2 or M1T2 thing. Now this is just based on SSS, so we can, guess what? I already had that in there. Okay, so now we need a T2. It could look just like T4. But it's no longer B, C, D, E, H, L, A. Okay? It is now all of these guys. We know that this is always non-null. So if we've got an M1T4, we really, really need the M1T2 for the next one. And of course, this is no longer defined. State underscore LUT2 for each one of the ops. I'm just going to grab all of these guys. Except it's a macro, so I don't have to do that. T4 becomes T2. So during M1, T2, this is a cleanup that is only called during phase phi2 rise. So I am going to have the phase here. Well, let's include this just in case. Okay, so AAA is equal to CPU, ECT value, and SSS is equal to, I will inline the crap out of all of this in a moment. Oh, for the macro, I actually need to have a value is equal to upper. This is not R. This is op. And FN. So at M1T2, this is where we're actually going to do the work. and Fn is going to have to control what happens in here. And for CMP, I need to not latch it into the ALU. And I need to worry about flags. You know what? I think this is going to actually have to call out to a function based on op. So this is going to call out to a function which actually does the work. Sorry, guys. Which means, really, I cannot macroize this. Because it's isomorphic to what I was about to do. So this is that. So what does it look like? It looks like static a static void I8080 underscore state underscore ALU T2 operation of I8080 CPU and int phase. Assumes we are in phase 5. No, that's not a sim. So how do I want to do this? If we promote things to unsigned, it'll make it easier for me to set the flags because I can look at a carry, which is higher. So unsigned ACT is equal to CPU arrow ACT arrow value. Unsigned TMP that's enough for me to... Keyboard macro is telling me that I messed up the indentation. Because I need to have one more of those. So we're going to say, search for there. We need a carry flag. Sub is CPU ACT minus temp. SBB is most of these comments are the worst kind of comments in the world, and they will go away. And temp. So this is complaining because these are after a label without a brace in front of it. CY is not available because it's actually the carry flag, which we haven't implemented. So we need flags. Let me bring up the PDF and let's go find ourselves the flag bits that the ALU update, that the ALU in the 8080 updates. So PSW, push and pop PSW, arrange the flag bits in a data byte. And this table doesn't tell us how they come together. So the 5-bit flag register contains, and there it is on the PDF, so I will be implementing these flags. Let's see, do we want to be able to trace the flag itself? I'm trying to envision whether this is going to be generally useful or if it's just something that I want to see. I think that if I want to track the the value of the flags, what I'll do is I will set up a sampler that looks at some other signal. Oh, I could set up a flag word as a data thing. So we need flags along with ALU and all that. Okay, that's got that. I'll go over to test. Okay, so we can look at the hex value in flags and decode it on our own, since we're just going to be using that for display. Okay. So next question is, what order do they appear in? And the flags are 0, carry, sign, parity, and auxiliary carry. We don't use C, we use CY for carry. 0 carry. Sign is SGN, let's call it S. Sign, parity, and AC for auxiliary carry. And now I get to track down how those bits are set up in the actual, oh, come on. If I try to drag it too high, Windows decides that I'm skipping over the other window and bringing the other window to the front. Not good. Not status bits. Probably have to go to the instruction set. Oh, wait a minute, here they are. So there's the official names, Z, CY, P, and S for the conditions. And we can look at CPS, CYAC, got it. So there's conditions for branches. Push PSW, here we go. So PSW says carry is in the low bit. And this is always 1. P is in the next bit. 4, 8. AC is at 1, 0. That's a 0. Z is in bit 6, which is 4, 0. And the sign is in 8, 0. Now this works out neatly because the sign bit comes from that bit of the accumulator, and the AC comes from that bit of the extended sum from the low 4 bits when we're adding and subtracting. And the rest of them just kind of get packed in appropriately. So flags reset is an initial value, and that bit will always be set right there. I have no idea why they did that. But we do need to mirror the push PSW. Okay, take the PDF down. So knit i8080.c actually I would call this flags init. Oh, wait a minute. The fact that that bit is set is something that's going to be enforced when we push because we might pop into it. So let's not do that. Let's just take that bit being set into account when we do the push. So CY like that. So the other thing is that CY is not exactly something I can add or subtract. Oh, it is because it's OX01. Okay. So flags. do I really want to have flags be the data item? Yeah, I think so. So anywhere we have set the flags, what I want to do is go back up to there. I'm going to say unsigned flags. We're going to scan down to phi to rise. I'm going to say flags equals CPU arrow flags arrow value. We're going to scan down to break. We're going to say data 2 of CPU arrow flags like that. So the CY stuff is slightly different. Now I could skip the switch because I know that this is only happening during phi 2. And I think as these are growing, that's not a bad idea. Okay, I blew the macro. So switch phase becomes void phase. Okay. Next. This guff needs to go away. None of these comments are interesting. So what is the best way to update flags? I'm just going to have to do it one at a time. This updates them all, so really I don't even need to load it up here. So basically ALU amper OX 100 parity. P is parity overflow, I think. We will have to get into how that is updated. I'm going to let the optimizer do a whole bunch of work here. Unsigned P is equal to parity. This is already in the right place. So back to the PDF. I need to understand how the instructions manipulate all of the flags. All instructions in this group affect zero sign, parity, carry, and auxiliary carry flags according to the standard rules. I don't believe, that's right, the 8080 didn't have an overflow. It's just a parity value. So there's several ways to compute parity. And there are tricks you pull when you're doing parity of long things like X plus, X masked with alternate bits set, add X shifted right 1 with all of those bits set. So that gives you that. You can repeat that for larger and larger fields until you come up with a sum, and then you take the little bit. But for 8 bits, it's easier to just have a parity table. So we have something called p-table, which I am going to set up here. Now we're going to compute the parity of I. Let's use unsigned for this. So we're going to use the mask add trick. Actually, we don't need a complete bit sum, so this is even easier. So the low bit has the parity of the low 2 bits. Now it has the parity of the and 4. Declaration of show. I thought that was in support.h. Oh, I don't have a show. I have a stub. I have a number of different macros that I use for that sort of thing. So this CY is a redeclaration. Fix it. Okay, and now we are not actually calling ALU init. Let's fix that. So what is this, like 0110, 1001, 1001, 01? That looks correct. So I can remove the stub. Now this series of operations, you know, I'm thinking that this series of ALU ops may be faster than doing a round trip to memory. So let's do that instead. How many places do I set parity? Oh, good God. So if I were to make this a macro or a subroutine, I would need to pass in the half carry bit, which would be and signed HC is equal to ACT ampere 15 plus TMP ampere 15. So this is ALU flags. I'm going to pass in ALU and half carry to get all of that stuff. So static void I8080 ALU. I'll let the optimizer make that into neat code for me. And this also means I can say flags equals, and that's going to blow up my, I was just considering getting rid of phase, but I'm not going to. That's going to blow up my CY stuff. So CY is going to have to be CPU arrow flags arrow value. So this guy is going to be used for everybody. So half carry only makes sense with add and ADC. But I do have to set it. Oh, and sub, right. And SBB. ANA and all these ALU operations store a 0 in the half carry. Okay, so one of the aha moments I had just while we were doing that was recalling that getting a overflow bit for the 8080 for a signed integer operation overflow is tricky because you don't have an overflow bit from the ALU. You have a carry bit and you have a sign bit. And I think it's the exclusive OR of the two. I'll have to work it out. Anyway, that was a problem for the people programming the 8080, not for people simulating it, because we don't have overflow. So what did this come down to? We've got a support function that sets the flags, which has to be handed the half carry, because it isn't there if you're just looking at the ALU. I'm including that 02 that's always set in the flag bit in flag word as you send it out, so that if we are tracing the value of flags, we'll see the 02 there, which means that inside i8080.c, actually, don't really want to initialize flags properly in CPU itself. What we want to do is here, where we are doing ALU init, I want to CPU arrow flags of that 0. Okay. So this is actually a stronger initialization than the real CPU gives us. I believe the real CPU leaves our flags by just what it was. What I'm going to do that. So what we're going to do is during initialization, we will modify the initialized value to assure that that bit is set. And I believe there are some other bits that are always unset. Push PSW, yes. The bits that are always cleared are 3 is OX04 and 5 is OX20. So those two bits are always clear. That bit is always set. So we're going to assert that. Now that's really just pandering to showing on the display what's going on. That's so when you do a push PSW, I look back and forth, I don't have to say, oh, wait a minute, the 20 bit isn't set. Oh, no. So 01, 02, 04, 08. It's the 08 bit. L1020, there we go. So 28. I'm going to put the support function all the way at the bottom. Following antique convention of forward declaring everything at the top, and then having the functions ordered top down within the source file. There were some people that ordered them bottom up within the source file, but they were looked at strangely, at least in the crowd I ran with. Because the internet was just coming into play, we did not have one homogeneous set of people that was the C community. What we had was a group of people centered around Stanford, a group of people centered around Berkeley, and a group of people centered around Murray Hill, New Jersey, and so on. Each one of these is major centers for who was doing interesting work on Unix and C. And then people would start to become part of that community as they dealt with code from that community. Then we started getting communities of people that were following the Borland standards, or God forbid, the Microsoft standards. So it was a fragmented community of communities. Anyway, so the group of people that I hung out with tended to order things top down within the file and carefully pre-declaring everything at the top, so you kind of had a function table of contents. Very useful. So half carries are all set. They're not consistently above or below the ALU. That's all right. And on the compare, compare needs half carry just like subtract does. There we go. And HC. So I'm assuming that compare sets half carry. All instructions in this script, add, ADI, ADC, sub, and so on, all instructions in this group, which means when we do, so increment register pair, no condition flags. Okay, DAA, all flags are affected. So DAA is going to decimal adjust the accumulator, assuming the previous operation was an add or subtract, using the half carry to adjust it to have the correct result. So we had two BCD numbers coming in. We did the add or subtract. We do a DAA to handle the fact that we needed to carry out at 10, not 16. Basically, it says if you have a half carry, you need to add 6. Basically. But I don't remember whether the rule for that is. Okay. It's written in the document here. If the value of the least significant 4 bits of the accumulator is greater than 9, or the AC flag is set, 6 is added. If the value of the most significant 4 bits is now greater than 9, or if the flag is set, 6 is added to the most significant bits. So we adjust for AC, and then we adjust for CY. So there's DAA. So when we get to that, the documentation here lays out explicitly exactly what's going on. Okay. ANA. Logical group. I'm going to double check. So given that these are 8-bit values, this is going to force the carry bit to 0, and that is correct. ANI, carry, and AC flags are cleared. So how would ANA have a carry flag, have an all AC flag? I think, I think they just didn't say the AC flag also for ANA. Okay, so compare. The Z flag is set to 1 if the two registers are equal. It is set to, and the CY flag is set to 1 if A is less than R. I think the other flags are set normally, so I'm going to continue with setting them just like subtract. They should have just said here that the flags are set as if you did a subtract operation, except that you don't actually commit the result to the accumulator. So notice on the rotates, where we're doing a logical rotate when we get to those, that these do modify the carry flag, but they do not modify the rest of the flag bits. So that's the ALU instructions for the 1-byte ALU instructions. Let's write some tests. So we're going to need an ALU program. We need to rewrite all of this stuff to not use MOV instructions. And rewrite all this stuff. So we need to write a decent BIST and a decent post. The basically are going to test to make sure that first of all we can get operands from any register, and second of all we can do any of the operations. And I think in theory we should be testing each operation and have it set and clear each one of the individual flags. So we need a result that's 0, a result non-zero, a result that's positive, a result that's negative, a result with a half carry, a result without a half carry, a result with even parity, and a result with odd parity. But we don't need each operation to do that. We do need to be careful. So for instance, half carry, we need to check the half carry on the add and ADC sub SBB individually. Oh, this is going to be a long one. Do I need to just go through this and exercise each instruction, just making sure that I use a different source register from time to time? We almost need a separate program to test each opcode. Yeah, I am going to defer this work. This is going to be a lot of just grinding out test cases. So if I'd been sane, I would have started out with let's do add, and I would have written the add stuff, and then I would have written the add tests. Instead, no, I had to do all 8 ALU operations at once. Oh. Sometimes I can be an idiot. So now I have the daunting task of writing tests for a huge number of things. Well, the one thing that I do need to do that I haven't done yet is I need to grab the opcodes for all of these instructions. So I'm going to grab these into a cut buffer somewhere. And we have this genopcodes.py. So for the ALU operations, our outer loop is going to be each operation for OO in range of 8. Okay, 4. So my operation, so I kind of forgot my PDF was up. Behind the PDF are the pound defines for all of the instructions we defined so far. Not important. So this is op is OX80 plus 000 times 8 plus SSS. Ops equals this. LU op of 000 and this. So if we go down here, we see that we now have all these opcodes being generated in a form that is completely useless to us. I need an underbar. And there we have it. So we have all of these guys, including the M instructions, which we have not implemented yet, but we're defining the name, just like for MOV. And all these are in numerical order, and they are from 80 to BF. So this is a quarter of our instruction space. I'm going to put the MVIs. I'm going to try to keep these in something like the appropriate order. There, sorted by numerical order on the opcode. Notice that MOV MM was in there. We're getting rid of it. I think I'm going to put in some blank lines before every line that starts a new one. So let's see, search for 0. There. That breaks up the blocks a bit. So going to need to generate test vectors. I wonder if there's an existing set of opcode tests. So Intel 8080 instruction set validation vectors. I am betting that there is no existing bit of 8080 assembly code out there that will tell you whether all of the instructions are working right or not. validating. And 8080 simulator. Oh, somebody has something called CPU diag.asm, which apparently does validate it. So we're going to go into the doc directory, CPU diag.asm. I'll put an 8080 in there in case I come up with one for other CPUs. Donated to SIG-M CPM Users Group by Kelly Smith, Microcosm Associates. Thank you, Kelly Smith. So, Simi Valley, they've got a modem. They probably don't have it anymore. It is Microcosm Associates CPU Diagnostic. So let's see, what does this do? On entry, it jumps to the diagnostic. So it's assembled to run at 100 hex. This is common for almost everything in CPM. You start it at the transient program area at 100. Below that, there's some stuff. So we've got BDOS entry to CPM, warm entry to warm boot, yada yada. They've got a message output routine. So when they call 5, that's going to go to something that's going to cause me to stop the simulator and do the right thing. Okay, this is sweet. So I don't think that I need to write extended tests of everything, but let's make sure that my basic functionality is there. So test vectors, make sure ALU instructions are not posed completely. Now I'm thinking that I can actually do some exhaustive testing on this. So instead of trying to write one big assembly code program that does everything, what I'll do is I will say I'm testing this operation with these operands, and I will generate the code in line. And I need to do that for each operation, so add. For each SSS in EHLA, not doing M yet. Set A to some test value, set SSS. We're going to need to test A versus A on its own. So for each, we're going to have a series of test values that verifies the results in flags. So flags to So to write all these out, then we're going to design some test vectors. So we know that the flag bits are being set properly because why? It's a central routine. I think we have to individually test for the values, the auxiliary value, the auxiliary carry. So compare A with itself. It's going to be a very short test. So there's our full test. And I got off track because I don't want to do a full test right now. I want to do just a simple test. Okay. So for those guys, we do need to do carry, set, and clear. Some operation needs to have a 0 result. Some operation needs to have a negative result. So parity, not clear to me whether the parity is even parity or odd parity. So somebody quoted some documentation here 6 years ago that the flag is set if the number of ones is even. There's also a suggestion that you not compute the value of the parity flag in the simulator, and instead you simply examine the ALU. That presumes that every instruction that modifies the ALU is going to set the parity flag. I believe that if you are popping the PSW, you could end up with a parity flag which does not correspond to the ALU value, which means we do need to set it. It needs to be set during the push. It needs to be restored during the pop. And we need to use what it is when we pop it, because the ALU, it's not going to recalculate. So I am going to calculate the ALU here. I'll calculate the parity. Okay. So this has been 2 hours. I don't have any tests yet for my ALU stuff, and I'm kind of running out of steam. So what I'm going to do is I am going to go offline. I'm going to add some comments to this code. I am going to send it on up to GitHub, and then I will think about the best way to test to make sure that these instructions are basically functional. I may or may not do a full test. I certainly want to get myself this CPU diag thing and work out how much of the CPU this checks out. How much of my testing does this take the place of? Now, I would like to pass this test, but I don't know how much other testing I can skip. So I'm just reading this real quick before I shut down. Instructions not tested are halt, DIEI, RIM, SIM, RST 0 through 7. So RIM and SIM are 8085 instructions, which don't apply to us. They're not going to test the RST instructions. It assumes that call and LXI SP works. Yeah, this is really, looks like a basic spot check. Oh, test move, INR, and DCR instructions. Nice. Okay, yeah, we will use this as our validation once we have enough instructions set that the validation runs. And I need to go chase down the assembler. I brought it over onto my Linux partition, but I didn't put it on the Windows WSL. Like I said, I'm bouncing back and forth between this and computer gaming during the day, so I'm just working under WSL for the moment. Anyway, that's it for this session. For me, it's comments and get the assembler and think about testing, and we'll be back when I am ready to do the next bit. Talk to you then. And until then, keep it